All right. Thank you, everyone, for joining the January edition of the Ice Giant System seminar series. Thank you so much to Dr. Patrick Irwin for giving the presentation today. I hope everyone had a lovely holiday season, hopefully got a chance to relax, recharge, recalibrate, to start the year off to a good start. So the way we do this seminar, if you haven't attended before, we'll have, I'll introduce the speaker, we'll have the presentation, and then at the end, we'll have a little bit of time for question and discussion, and then we'll do a little bit of a community update, give information about job postings, upcoming meetings, and whatnot. So on that note, welcome to Dr. Patrick Irwin. Prof. Patrick Irwin received his doctorate of philosophy on remote sensing of Martian atmosphere from the University of Oxford in 1991. After a brief spell working for a computer company in London, he returned to Oxford in 1992 and became a lecturer in 1996, subsequently becoming a reader and then professor in 2011. Prof. Irwin was a co-investigator on the Cassini, Sears, and Rosetta Virtus instruments and was a team member of Galileo and NIMS. He is the originator and lead developer of the Nemesis radiative transfer and retrieval code and leads a program of ground-based spectroscopic observations and interpretation of solar system planetary atmospheres. In recent years, he has devoted much of his time to the study of the ice giants, but as a co-investigator of the MAGIS instrument on ESA's JUICE mission to the Jovian system, he is now concentrating his research more on Jupiter's atmosphere. But today, he is here to talk to us about ice giants' atmospheres, and specifically the clouds, storms, and colors of those atmospheres. Take it away.
Right, thank you. So good morning to you folks over the pond, and hello to you chaps over here, and Happy New Year. So today I'm going to talk about cloud storms and colours of the ice giant atmospheres, summarising work I've done since 2018 in a few papers studying the atmospheres of these planets. So as you know, the ice giants are very similar in some ways. They have very similar mass and similar radius, but very different than others in that Uranus has this really weird high obliquity and appears to be almost in complete thermal equilibrium with the sun. Whereas Neptune, we know, radiates a lot more heat away from than it receives from the sun and has a normal-looking obliquity. And some of the key sort of questions that remain to understand its atmosphere is, why are these two planets so different? Why does Neptune have lots of internal heat and a vigorously circulating atmosphere, whereas Uranus appears sort of a bit dull and sluggish? They, in fact, both have very similar temperature and gaseous compositions, so shouldn't their clouds be very similar? Why is Uranus tipped over? Methane is predicted to condense in both atmospheres at about 1 to 2 bars, and we know there's a lot of methane, and so you might expect there to be a massively thick methane cloud, but we don't see that in either planet. Finally, what are the dark spots that we see occasionally in the atmosphere of Neptune and sometimes Uranus, and why are Uranus and Neptune slightly different colours, or indeed are they slightly different colours? We'll work through that during this talk. So this is a comparison of the visible spectrum of the sun compared to Uranus and Neptune. I'm just showing this mainly just to see that you can see just from the visible spectrum that Uranus and Neptune has a large amount of methane in its atmosphere, because you can see strong absorption bands of methane near 550 and 620 nanometers and so on. And so it was known quite early on that methane was a major part of the atmosphere. Though when I say major, I mean, most of the visible atmosphere is made of hydrogen and helium, as you know, and the amount of methane is somewhere between 1 and 5%, depending on which estimate you look at. But of course, methane should condense in the upper atmosphere and should, we thought, give rise to thick clouds. If we now, methane is a very obviously it can condense. It also absorbs sunlight, and it absorbs sunlight in those bands I showed you in the visible. But as you go to longer wavelengths, it absorbs more and more. And in fact, this absorption of methane is what makes these planets have a stratosphere, in that the light is absorbed by methane in the high atmosphere and gives rise to a clearly defined tropopause. I'm comparing the this is the mean transmission of the Uranus atmosphere from 400 nanometers out to 2.4 microns. And you can see that it's very clearly visible, and then there's these strong absorption bands as you go to longer wavelengths. And on the right here, if I press play, this is an HST STIS observation, which has been turned into a disk. And as I press the movie, we're going to go through different wavelengths. So the mean reflection spectrum is here on the bottom. The current wavelength in nanometers is here, and the image you'd see is there. And so if I press play, hopefully, there we go. As we go across, we see in the short wave, we're seeing mostly radius scattering. But then as longer wavelengths, we can start to see deeper, and we start to see the deeper clouds and haze layers. And so you can see in this case, measured in 2000, we have the appearance of the polar hood near the South Pole, and other features which are at different altitudes. I mean, the takeaway point from this is that at different wavelengths, because you have a different amount of absorption due to methane, you can see further down to the atmosphere or less far down to the atmosphere, depending on the amount of methane that's there. And so if I just stop that and move it to a point here where there's lots of methane absorption, you just see light from the hazes. Where if I go to here, where there's little methane absorption, I see deeper down, and at some wavelengths, then I see more of the polar hood. And so by analyzing the reflection spectrum of Uranus and Neptune, you can work out what its vertical structure of aerosol is. So to do this analysis, I'm using, as I said, I'm the developer of the Nemesis retrieval suite with a very sort of unlikely acronym, the Nonlinear Optimal Estimator for Multivariate Spectral Analysis. Very long, complicated story about why we came up with that name, but it's I won't bore you with that. But it was originally developed for solar system studies. Originally developed to look at Cassini-Sears observations of Jupiter, Saturn, and Titan. But it's since been extended to do exoplanetary observations as well, and direct imaging, and is a very widely used, not reasonably widely used toolkit because it can analyze the light from any planetary atmosphere. As I say, it was designed from the start to be generally applicable, and was originally designed for use just with a correlated K-Ford model, though since then we've moved on to do line by line and other methods as well. The model handles thermal emission and scattering, both multiple and single scattering, and its original core retrieval code is based on optimal estimation, and is written in Fortran. Fortran. Since most people find that untenable these days, we are currently rewriting the whole thing into Python, and this is. Oh, I should have said the original code is available on this. We're writing Nemesis currently into Python and also implementing a nested sampling algorithm. And the new version, which we are calling Arch Nemesis, will be available shortly. I'll keep you posted on that, but hopefully that's going to be available soon to everybody, and will hopefully keep Nemesis alive into the 21st century. So back to Uranus. So Voyager 2 flew past Uranus in 1986 and revealed an almost featureless dead world with few discrete clouds. And because there wasn't much to see, people thought it was a bit dull, really. But in fact, that turns out not to be true. When Voyager 2 flew past, it flew past near the one of those summer solstices, and it just turns out that at that season, the atmosphere is a bit quiescent. But as we've moved on towards the equinox in 2007, and then onwards now, moving now towards the north summer solstice, you can see there's been an awful lot of activity in the atmosphere of Uranus, with especially during the equinoctial times, these discrete storm clouds appearing at mid-latitudes. And also you can see that in 2004, we've got the remnant of the South Polar Hood, which covers the sun-facing hood. And this was dying away during this period, and a new hood forming at the North Pole, which has since, starting as a sort of collar around sort of 40, 45 north, and since extending towards the pole, so that now there's a well-established North Polar Hood. And what have we learned? Well, we've learned an awful lot of things about the atmosphere of Uranus and Neptune during this time. So when you look in the near infrared and these methane absorbing windows, you see this increased reflection at the poles. And this was initially interpreted as being caused by an increased amount of haze at the poles, which we know is true. But it turns out actually that's not the whole story. The reason why Uranus appears brighter at the poles is because there is more haze, but it's also because there's much less methane there, by around about 50%. And this has been seen, and this was detected in HST STIS observations by Eric Kokoschka and his colleagues back in the late 2010s. And since then, we've reconfirmed this by using observations with the MUSE instrument at the Very Large Telescope. And I've shown here some plots from a paper by one of my graduate students, Arjuna James, and one by myself, looking at Uranus and Neptune, where we've retrieved the same latitudinal variation in the abundance of methane. Now, why is this? I mean, this has given rise to this overturning circulation models. An example here is from a paper by Lee Fletcher in 2020. And the idea is that we think that by and large, at deeper levels near the equator, air is rising up and bringing sort of condensable gases like methane up to the atmosphere, and then that air moves sort of polewards at around about the 1 bar level and then descends at the poles. And so that would explain why there's more methane at the equator and less at the poles. It's thought that this overturning circulation system may be stacked, and so that in the upper cell drawn here, you can see that the flow is reversed with subduction at the equator and rising at mid-latitudes. There's an awful lot that's not understood about the meridional circulation, but certainly mapping the distribution of gases like methane gives us a window into that, and does seem to support the idea that deeper down, air is rising at the equator and descending at the poles. At longer wavelengths, and this is near 1.5 microns, we did some observations with the NIST instrument at Gemini North. And it turned out that at this wavelength, and this is on the left here is the scanning through the observation. NIST is an integral field unit spectrometer where it records these images over 3 arc second by 3 arc second field of view, and where each pixel is a complete spectrum. And again, in this image, the numbers here are the current wavelength. This time 155 means 1.55 microns, and you can see there's a strong reflection band at 1.5 and then a strong methane band at longer wavelengths. And as we go through, you can see different cloud features at different levels. What we also realized in this wavelength range is, especially around about 1.58 microns, is that there is an absorption band of hydrogen sulfide, which had never been observed before. And we were able to measure that and fit to that, and so make the first detection of hydrogen sulfide in the atmosphere of Uranus, and almost certainly in the atmosphere of Neptune as well. Now, why that's important is that we know that there's hydrogen sulfide and ammonia deep down in the atmospheres of these planets, and at some level, these gases are expected to combine together to form a cloud of ammonium hydrosulfide, and that would leave then the more abundant molecule alone to go up and condense at upper levels. On Jupiter and Saturn, we know that ammonia is more abundant than hydrogen sulfide because all the hydrogen sulfide is gone by the time we get to the cloud tops of Jupiter, but we still have lots and lots of ammonia. So for Uranus and Neptune, we weren't entirely clear whether the upper level clouds we would see would be of ammonia or hydrogen sulfide. But by detecting hydrogen sulfide in the reflectance spectrum here, we know that hydrogen sulfide is left, and hence if there is a cloud in the upper levels, it should be made of hydrogen sulfide rather than ammonia. This is also relevant to possible future probe missions to Uranus and Neptune, in that hydrogen sulfide is a much less strong absorber of microwave radiation than ammonia, and so in terms of having a spacecraft communicate back to the orbiting spacecraft, it's much easier to design a probe mission to go to these planets if most of the gas, well, if there's not much ammonia, but just a bit of hydrogen sulfide. And so this was an important discovery, and one I was very glad to be able to help make. It also gave rise to some interesting press coverage. This one from a satirical TV program in the UK called Have I Got News For You? I was watching this with my family on a Friday evening in April 2018, and it's one of my, I like this program, and I was very, 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 very happy when this appeared up, because my work actually made it into popular culture. Less happy with this one, but then you can't have everything. So at least people were interested, and we made some impact. Now, so we've detected hydrogen sulfide now on Uranus and Neptune, and if you do some first order sort of ad hoc mapping of that, we see this distribution for Uranus up here and for Neptune down there. And so we see the strongest signal of hydrogen sulfide at sort of polar latitudes for Uranus, and this is the map compared to the geometric description of Uranus at the time, and this is for Neptune. And so we see, certainly for Neptune, we see apparently more at the South Pole than the equator. And that's confusing because from the overlying circulation model, we would expect it to be the reverse of that. We would expect there to be more hydrogen sulfide at the equator and less at the pole, just as we see here for the methane maps I showed you earlier. And also over here, this is in radio microwave maps from the VLA in places where a higher brightness temperature indicates a lower abundance of ammonia and hydrogen sulfide. So certainly from the expectation from the methane map and from the observations at longer radio wavelengths, we expect there to be more hydrogen sulfide at the equator than at the pole. So we're not quite sure why this is, and we're currently going back to look at these data, and in fact these NIST data are currently being reanalyzed by one of my current DPhil students, Joseph Penn, and he's making a great inroads into figuring out why this appears to be inconsistent. Going on more generally to look at the atmospheres of these planets, I mean, in previous studies, there have been all sorts of models of the vertical structure of aerosols in these planets. And there have been some ad hoc models generated for individual observations over narrow wavelength data sets, and things like limb darkening has sometimes been overlooked. However, all these studies find a thick sort of cloud or haze at about 2 or 3 bars, and an extended stratospheric haze, but it hasn't been very easy to take any of these models and extrapolate it to other wavelengths. It's also a horribly degenerate problem. If you're trying to pick out methane variations and cloud variations from these spectra, it's not easy to constrain a robust solution. So in 2022, I set out to try and reduce this degeneracy by analyzing data from as many possible sources as I could simultaneously, and using limb darkening observations to constrain the scattering properties of the aerosol hazes, and also using as wide a wavelength range as possible to get a better constraint on the particle sizes of the aerosols. And in the study, we analyzed data from Hubble spacecraft STIS, Gemini NIFS, which I talked to you already about, and also the SPECS instrument at IRTF. So as you know, Hubble Space Telescope launched in 1990 in a low Earth orbit, a 2.4 meter mirror, and one of the instruments is the STIS, Space Telescope Imaging Spectrograph. And this is a combined imager and spectrometer, which covers 115 nanometers out to 1050 nanometers. And it observed Uranus and Neptune in 2002 and 2003. And this was used by Kokoschka and Tomasko to figure out the latitudinal variation of methane. It produces images like this. I showed that already for Uranus on the left, and on the right is Neptune. And so this is going, oh sorry, I beg your pardon. On the left is HT STIS, on the right, sorry, is Gemini NIFS, going from 1.5 to 1.8 microns. And so we have this integral field unit spectrometer observations of the reflectance spectrum of both planets. In addition, we had NASA Infrared Telescope Facility SPECS observations. So this is at Mauna Kea, 3.2 meter mirror, built to support Voyager missions, but provides continued ground-based support to missions and an amazing sort of archive of observations of the solar system planets. And SPECS itself is a medium resolution spectrograph covering 0.7 to 5.3 microns. And we used archived long slit spectroscopy observations from 2000 for the study, where the slit was placed on the central meridian, and we averaged overall latitudes for both Uranus and Neptune. Finally, as I mentioned before, slightly out of order, this is the Gemini North and the NIFS instrument. This is an 8.1 meter mirror. It has adaptive optics at Mauna Kea. And as I say, the NIFS is a medium resolution integral field unit spectrometer covering 0.95 to 2.4 microns. And for that, we used observations made in 2009 and 10. So this plot compares the mean reflectance spectra of Uranus and Neptune along the central meridian. On the top, I've taken the HST STIS observations and just averaged it along the central sort of line of the planet. And black is Uranus and pink is Neptune. And on top of that are the sort of standard sort of response curves of the human eye cone receptors with the blue, green, and red. And so you can see that actually the spectra of these two planets isn't very different. I mean, it is, yes, Neptune is slightly more blue, but not an awful lot more blue, according to this. And then on the bottom, I compare that then with the observations from RTF specs, which go from 0.8 microns out to 2.5 microns. And as you can see, for Uranus, the signal noise kind of runs out at about 1.8, but for Neptune, it goes a bit further because there's a lot more, there was more reflectance at longer wavelengths for the Neptune observations. So we fitted to these data simultaneously, and to do this, we took all the observations for HST and STIS, and we measured their limb darkening curves using, we fitted the limb darkening we could see at each wavelength to a Minert model, and from that Minert model, we were then able to reconstruct the spectrum you should see, the mean spectrum you would see at different zenith angles. And so we generated synthetic spectra at zenith angles of 0 and 61.45 degrees. Why 61.45 degrees? Well, we're modeling this with a multiple scattering model, and we wanted the zenith angle to coincide with one of the angles we use in our zenith angle quadrature. And so we're using a 5-point Gaussian-Lobato quadrature scheme, and 61.45 degrees was one of the angles. And so we chose that as the angle. And as you can see, we can, comparing 0 and 61, you can see that there's limb darkening at short wavelengths, but some of these longer wavelengths, you can see there's limb brightening. You can see that the spectrum at 61.45 is brighter than the spectrum at 0. On this side, this is the Gemini NIFS observations. I should say in both cases, the grey points here, the grey data here is the synthetic measurement, and the red and the blue lines are our fit to that with our model, which I'll tell you about in a second. And you can see here we're getting a very good fit to the data. Similarly over here we have Gemini NIFS, and we fit very well in the peaks, not brilliantly, but not too bad in the absorption bands over here. And finally, this is the RTF specs observation, where grey is again the observation and red is our fit to it. And this is the line average spectrum. And we generated a model to fit all these data simultaneously, and so come up with a cloud model that would fit all these observations. And that was a cloud model which had different sort of vertical layers. And also we retrieved the scattering properties of the particles directly by assuming we could retrieve their imaginary refractive index spectra and then use a thing called Kramers-Kronig to generate the real part, and then calculate all the scattering properties using Mie scattering theory. This is the same process applied to Neptune. And so what we came up with is this model. We developed a new holistic model which can simultaneously fit spectra and the limb darkening from 0.3 to 2.5 microns for both planets with a self-consistent model. And basically this model consists of 3 parts. There's a deep component, which we called aerosol 1, which is at pressures greater than 4 bars. There's a middle component, which is called aerosol 2 at 1 to 2 bars, and an upper level haze, aerosol 3, at pressures less than 1 bar. In addition, for Neptune, we also had to have an additional sort of component from methane ice at around the sort of 200 millibar level. The haze layers we found need to have strong UV absorption and strong red absorptions, so they're not really consistent with a composition of pure ice. And yeah, we found these haze layers to be really quite reasonably well uniform across the planet. And our main sort of contributions to this is that we posited that at the methane layer we have this layer of we think that haze has been generated in the upper atmosphere. The haze particles are sort of trickling down through. They're kind of bunching up at the 1 to 2 bar level because there's a region of vertical static stability because at that level the mean molecular weight of the atmosphere drops rapidly as the methane condenses, and so that gives you a stable, it's like oil over water. It's a region of static stability. And so we get a haze layer building up there. And then we think that any methane that is sort of convected upwards, as soon as it sees this this haze layer, all the methane that's there will condense onto the haze particles very, very quickly, form large particles, which will immediately drop out as ice and snow. And so that explains why we don't see a thick methane ice cloud at the expected condensation level. This ice snow will, as it drops down, it will re-evaporate, and so that will then leave its photochemical haze particles free to then act as condensation nuclei for the next level of condensation, which we assume to be hydrogen sulfide. So we assume basically there's a hydrogen sulfide stroke haze layer around here, around about 5 bars. We've got this sort of haze layer at 1 to 2 bars where methane ice is condensing, and this upper level photochemical haze. An unexpected outcome of this model was that when we generated the colors you would see, we found that Uranus and Neptune would actually look pretty similar color, which is kind of what we expect from looking at the spectra I showed you earlier. But this is completely contrary to what is generally thought of, from the Voyager missions of Uranus being sort of greenish blue and Neptune being very dark blue. So that led to the question, have the colors actually changed since the Voyager observations in 1980, or have we missed something in terms of the processing of these data? Colors, God, to turn spectra into colors is an absolute rabbit hole, and just taken a lot of my time to unpick exactly what goes on. The eye perceives color via the tri-stimulus response of the short, medium, and long cones in the eye. And that means that because you're only looking at 3 sort of broad filter bands, it's not a unique sort of representation of color. You can have several different shaped spectra which will give you the same long, medium, and short responses. Also, when you're looking at the screen here, when you're looking at your screen right now, the projectors and monitors that recreate images are doing that with 3 narrow filters, LEDs, red, green, and blue, typically at 645, 526, and 444 nanometers, but not always. And what the monitor tries to do is try to give you the right balance of red RGB that would give you the same perceived color as the real object. And so you have to sort of then, so to do this, you have to sort of take real colors and figure out what combinations of red, green, and blue will give you the right effective same color. And usually for most colors, so you compare combinations of RGB against monochromatic light. Normally you can do it with a positive combination of each. For some colors, actually, you can't do that. You have to add the RGB to the test color in order to get a balance. And so such colors are called out of gamut. Also, for the RGB responses of these monitors, they're not unique. This is a spectra I took of 3 different monitors that I have around the department. And as you can see, that they're all RGB. They're all supposed to give you the same color when you put the same image into it, but they have slightly different RGB responses. And so not all monitors are the same. Because of this, the combination, there's an average human eye, because there's RGB is not actually standard, there's an internationally agreed system called XYZ, which is analogous to RGB, but there the color matching functions are all positive. And so you can take any spectrum and you can turn it into XYZ, or XYZ as you guys have the pond would call it. That's a representation of color. And then there's just linear transformations you can use to convert then to other color systems like sRGB. So that's the first thing you've got to figure out when you're trying to represent, to take a spectrum and turn it into a color image. The second thing is intensity. The human eye does not respond to intensity linearly. We are obviously very interested to know what's lurking in the shadows, and so our eyes tend to work in a response given by this function here, where it's called the gamma function, and the upshot is that even when something bright in the field of view and surrounded by a dark thing, if there's small changes in the dark thing, you're going to see it because that could be the tiger that's about to leap out and kill you. That's why the eyes evolved to be like that. And that has to be taken into account when you display an image. Now, camera CCDs, they are linear, and so they will record the linear intensity that arrives. But if you were to digitize that camera signal directly, you would end up having, you'd waste bits on the bright parts of the image and not have enough for the faint parts. And hence cameras almost always multiply the pixel responses first by a gamma function and then digitize it, which gives you a much more efficient gamma encoding, and that's shown on the top right picture there. However, this is hidden from you. This is not normally something you're aware of. Then to produce that image on a screen, the monitor or the projector or the printer, that actually needs to apply the inverse gamma function to make it look right. And this is present in all display devices, but again is hidden. You don't know it's there. And so images from a camera are automatically gamma encoded, and so your monitors are automatically gamma decode in order to get the right brightness across the image. So when I first started this project, I assumed that if I filled a screen and said, okay, set all the pixels to 255, and then I took another screen and set it to 128, the intensity of the 128 should be half that of 255, right? But no, because that ignores the fact that there's a gamma correction hidden in your monitor. This plot here is trying to show that. I've got on the left is a region of half white, half black. And if you squint your eyes up, you should see that the brightness of that, mean brightness of this, is more like this, the right-hand image, than the middle one. Whereas the middle one is I've set all the pixels to 128, and on the right one, I've used the gamma correction, or rather, I've accounted for the gamma decorrection. And so if you take that into account, then you get the right variation of intensity across the screen. Right. So taking all these things into account, I went back to the original Voyager observations and reprocessed the observations to turn them into true color, as I perceive true color. And you can see here that I'm comparing here the original Voyager 2 colors with the recalculated colors, and you can see that yes, Neptune is bluer than Uranus, but not by that much. And so actually the colors have not changed that much since Voyager. The blueness of your Neptune that we're all aware of is due to the fact that an enhanced color set was used, and this was chosen right at the beginning of the mission in 1989. I've seen a press conference where images were put up, one sort of true color, one like this, and because this sort of color scheme shows all the features in Neptune's atmosphere much more clearly, this is the one that was chosen to go out to the wider world. And people just assumed it was true color, and the idea that Neptune is dark blue just persisted and persisted and persisted. In fact, it is bluer, but not that much. However, the color of Uranus has changed since Voyager, because during that time, or rather during these observations, you can see that this is HST WIFC observations, WIFC3 observations from 2014 to 2022. Drawn lines of latitude at 0 and 35 north. And you can see that during that time, the pole has swung towards the Earth. And because the pole is brighter, because there's more haze, the overall color of Uranus has actually changed during that time. So there is a seasonal change of Uranus's color. And this can be seen much more clearly in observations that are made by the Lowell Observatory from 1950 to 2016 by Lockwood, by Lockwood. And this shows the integrated, well, he measured the magnitude of Uranus at 2 wavelengths, Stromgren B and Y, which are actually blue and green. And I've plotted the data here in terms of the equivalent I of F of the planet. And you can see there's a seasonal variation in color, much more at green than at blue. And we then used our models trying to figure out why that is. And we came up with a model where if you were to add a contribution of bright scattering particles to the aerosol 2 layer, that's the one at 1 or 2 bar, then you are able to pretty much reproduce the green variation of reflectivity with the year, certainly from 1986 onwards, and sort of the blue part. It's not brilliant, but it's not bad. There's also some change. However, neither model works very well from 1950 to 1980. Why that is well, there are some ideas we have for that, but I don't have time to go into that now. Finally, dark spots. Dark spots have been well known on Neptune since the Great Dark Spot was discovered in '89. This has since disappeared, but several new spots have since appeared in HST imaging. However, the Voyager and HST images were only measured at a few discrete wavelengths, and so it wasn't really very clear at what level in the atmosphere these dark spots was. In 2018, a new spot was seen by HST called NDS 2018, and as soon as it appeared, we applied for time to use MUSE to observe Neptune, and we won time in 2019 to do that. And so the idea was then we could measure the spectrum of a dark spot, and from the spectral signature, hopefully discover more about where it is in the atmosphere. So this is the MUSE instrument. This is an IFU, and this is a lovely graphic that the ESO people put together, showing the appearance of Neptune at different wavelengths as you scroll from 475 to 933 nanometers. And again, as we go through these different wavelengths, we're probing higher or lower in the atmosphere, and so we can work out the vertical structure of the aerosols. So we were very excited, got time, and then we processed the data, and this is our image of Neptune at 551 nanometers, where we expect the dark spot to be visible. And I can tell you that the dark spot is just here, but we couldn't see it. Because even though MUSE has fantastic adaptive optics, it wasn't quite good enough to actually just pull out the spectrum of the dark spot. So we had to go back to the drawing board and actually figure out a way of sharpening up this image, and we tried all sorts of methods. But in the end, we had to develop our own ad hoc sort of method based on techniques used by the radio astronomy community. And if we apply that deconvolution to this, then we start to see this image. And there you can see this dark ring around the South Pole, which is reasonably clear. And you can start to see, a slight hint of a feature just here, which is the dark spot. And then if we enhance it and stretch, then you can see that here's the South Polar wave again, and here's the dark spot. So by deconvolving these data, we were able to then actually isolate the spectrum of the dark spot. In this plot, I've got different observations at 551 nanometers is obviously in the green, where we expect the dark spot to be most visible. 831 nanometers is a region of very strong, is a region of where the atmosphere is very clear, so the methane absorption is very little, and so you can see deep down in the atmosphere. And 848 nanometers is a wavelength near to there where methane absorption is strong, and so we can only see only into shallow heights in the atmosphere. And there are different cloud and dark features here. You'll notice on the left there's these bright sort of regions. These can't quite see them here, but you can see them at 831 and 848. The fact that we can still see them in strong methane absorption tells us that they are high. And if we look at the difference in the spectrum of one of these spots compared to the regions around it, you can see that they are, there's more reflection over a wide range of wavelengths and without much absorption features of methane. So we know that these are high altitude or shallow bright spots. If we look at the dark spot and look at the difference in the spectrum between it and the regions immediately around it, you see that it's dark in the red, in the green, with these quite strong bands on top of it due to methane absorption, and then there's almost nothing at longer wavelengths. So we know that whatever it is, it's only visible at a short green and blue wavelengths, and because of these strong bands, we know that it's deep. Finally, there was this weird spot just next to the great dark spot, not great dark spot, the dark spot here, which you haven't noticed before in any other observations. If I put a spotter over there, then this is the difference in that spot and regions near to it. And you can see that this spot is not visible in the 848 nanometers, but is at 831. And if you look at the different spectrum, you see that the reflection spectrum is limited to narrow peaks at wavelengths of very low methane absorption. So this tells us that there's a brightening of the deep cloud, which is causing this spot. So we call this a deep bright spot. So putting this all together, it's the first ever spectrum made of a dark spot. The spectral signature is very, very distinctive and shows it must be deep in the aerosol 1 layer, which we think is the hydrogen sulfide layer. We also saw this new feature, DBS 2019, and we think this is also deep in the aerosol 1 layer. And as it's right next to the dark spot, presumably has something to do with its formation. We see that both these features are very different from the shallow bright spots, which we saw on the left-hand limb. The important thing here is that only spectral imaging where we measure the images at lots and lots of different wavelengths. Only spectral imaging can help you tell the difference between shallow and bright spots. Also, one thing that came out of this is you can see that at 831, there's this quite regular band of bright and dark with a wave, sort of a latitudinal scale length of about 20 to 25 degrees. This is not seen at any other wavelength. As far as I've seen, has not been seen before at all. And this points to deep variations within the latitude of the hydrogen sulfide cloud. The data are visible in some images shown by in the paper by Chavez et al, but it wasn't drawn attention to. And you know, it reminds me of sort of the when you look at Saturn in the visible, you see sort of broad features. But when you look at 5 microns, you see discrete features due to variations in the cloud decks deeper down. And this speaks to me of there being sort of a sort of variation in the cloud at the hydrogen sulfide layer, which is somehow producing a sort of this latitudinal variation, which is very interesting and certainly merits further study and investigation. Finally, into the future. So James Webb obviously is up in space. And observations were made of Uranus and Neptune with MIRI and with James Webb with NIRSPEC. And these go from 1.6 to 5 and a bit microns. The analysis of these data is ongoing, and papers are in preparation, with Mike Roman about to release a paper anytime soon on Uranus and then Neptune. And the good news is that our holistic model has mostly survived, but the aerosol 3, we're finding now that this upper level haze, stratospheric haze, rather than being a continuous distribution, we're finding it's actually more consistent with a vertically confined layer near the sort of 200 millibar level. Sadly, these the NIRSPEC observations didn't go shortward of 1.6 microns, and so we couldn't use them to discover more about the hydrogen sulfide variations. And so we've made repeated proposals for general observing time to cover this missing wavelength gap. We've put one in again for cycle 4, and we're crossing our fingers and hoping that we get that time, because certainly looking at the James Webb data from longer wavelengths, the data quality is fantastic, and we should be able to really nail the hydrogen sulfide problem with these data. Finally, I'm currently working on a project to look at revisiting the bond albedo of Uranus and revisiting the question of whether Uranus is in thermal equilibrium with the sun or not. And we're working on a paper which is approaching the state where we can submit it, but not quite ready. And that's it. So thank you.
All right, thank you so much. Everyone, please put your virtual claps in. If you have questions, feel free to put them into the chat and I'll read them out loud, or go ahead and raise your hand and we'll call on you. I already see one in the chat from Sean. Are the dark spots essentially holes in the hydrogen sulfide or thinner regions, or something compositionally different, or aerosol particle differences?
Yeah, we know they're not holes. It's not due to a thinning of the H2S cloud. It's definitely due to a darkening. Change in the sort of reflectivity spectrum of the particles. That was the quite strong conclusion of the analysis we did on that. And so that points to there being more sort of chromophores in that region. Whether that's due to photolysis, some new gas coming up and being fertilized to make dark particles, or whether it's due to maybe local heating, which might sort of evaporate hydrogen sulfide from a deeper dark haze core, we don't know. But it's definitely a color change of the aerosols rather than a thinning.
Okay, while we're waiting for other people to think about some questions, I have a question. So I'm not an atmospheres person. I'm a hard surfaces person. So the color discussion that you gave was really interesting. I saw there was a picture that you showed from Hubble of Neptune that was also a pretty dark color, similar to that first picture of Neptune that you showed. Does that have the same issue?
Do you mean this one?
Yeah,
Yeah.
that one.
So this was a they measured in a few filters and they put it together to make something that was consistent with the expectation of what Neptune would look like.
Ah,
So this was done before I revisited the general color problem.
very interesting. We have a question from Megan Russell. First, Pluto gets reclassified. Now Neptune isn't actually dark blue. I feel like my childhood was a lie. Are there any atmospheric models that could explain the banded features of hydrogen sulfide that was shown 1 or 2 slides back?
Not that I know of, and I'd love some input from dynamical modelers to figure out what this is. My speciality is taking observed spectra and inverting them to get the most likely sort of solution from there. But in terms of interpreting it, you need to actually have some model of atmospheric dynamics and all the interactions with heating and cooling and things. And so I don't know the answer to that, and I'd love somebody to tell me what it is.
We have another question from Gracie Davide. Do you think that our models for CH4 and H2 CIA are adequate to model the ice giant spectra?
Hi, Davida. Well, we're currently looking at that. I mean, it's the CIA is, we think, reliable at shorter wavelengths. We're currently having problems trying to fit James Webb observations at longer wavelengths, and we think maybe that's due to gaps in the CIA observation CIA data sets. I mean, you can't have data sets which are too good to analyze these things. I mean, every time the methane or hydrogen sulfide or ammonia data sets gets improved, that means you have to revise our estimates of the that we get from analyzing spectra. And so there's certainly, I think the CIA is certainly something that could be and should be improved to help us understand these spectra.
All right, we got lots of questions from Glenn Orton. For the Uranus bond albedo, is the progress you intend to make an update or a refinement of the phase curve or something else?
It's a bit of both. It's basically, I've taken the seasonal model I showed a couple of slides back, and I've just basically used that to work out what the the bond. So the difference between geometric and bond albedo is that geometric is the reflectivity back to the line of back to the observer, whereas bond is the total reflectivity in all directions. And because we have a model that we use to simulate the appearance of Uranus at any angle, I was able to calculate what the bond albedo would be, and because I've also got a seasonal model, I'm I can run that forward over a whole year, and so work out what the orbital average of the power absorbed by Uranus will be. So that's currently in progress, and as I say, I'm hoping to get that in a state where I believe it in a few weeks' time.
Question from Martin Roos Sarote. I apologize for the pronunciation. Would images from, say, the icy moons or Io also look much different if reprocessed?
Good question. I don't know. I assume. I mean, turning, because when these images, you measure in different sort of filters, and you take those different images and you combine them together to give you your expected net color. And so there's an awful lot of devil in the detail with these things. I've not thought to look at that. I mean, what you need to be sure is you need to have a continuous spectrum of these things in order that that if you do measure at a few different filter wavelengths, you can compare that to your expected continuous spectrum, and from that generate an RGB response which is consistent. So it's not something you can do directly from the images, and you need a model from another source which has continuous spectra to be able to fill in the missing gaps and hence generate a really reliable and robust color representation.
A question from Henry Garrett. Can you detect the aurora? If so, can you determine the magnetic poles critical for radiation belts?
Not at these wavelengths. At longer wavelengths, possibly. And I think that that's something that James Webb may be able to shed some light on.
Question from Daniel Wenkert. How do Voyager 2 limb darkening curves, especially in violet and green, compare with modern spectral limb darkening curves convolved with the spectral response curves of Voyager 2 cameras and filters?
So that's one of the things that we've done in this the new work I'm currently working on, and the phase curves are, you know, they have a very similar shape. The absolute photometric calibration of the Voyager data, I think, is possibly needs to be revisited, but it's not the simulations we're getting of the phase curves are to first order very similar to the measured phase curves from Voyager.
Excellent. And I have one last question. So can your model, have you or could you apply your model to some of the moons or planets that have atmospheres that are not the giant planets, such as Titan or Venus? Would there be a utility in applying your model to those bodies?
What, in terms of working out the color or interpreting vertical structure?
Both.
I mean, yes. I mean, I'm not. I mean, I've been involved in a couple of Titan studies at longer wavelengths. I've not been involved too much in the near infrared, but certainly the same models we're turning to look at Jupiter and Saturn now, and this idea of the and I think there's lots. I think there are a lot of similarities to the atmospheres of Jupiter and Saturn that could be potentially sort of captured within a sort of a simple model that would hopefully fit both together. And so currently working to generate a set of archive data, again covering as wide a wavelength range as possible, to see if we can figure out a more robust vertical structure model of Jupiter and Saturn.
Interesting. Okay, well, I don't see any more questions coming through on the chat or any hands raised. So I'm going to turn it over to Jody. Pat, if you wouldn't mind stopping your share, and we'll turn it to Jody to talk a little bit about some community news.
Sure, yeah, and thanks, Pat, for a really awesome presentation. Like Mallory, I loved the conversation about like the kind of color theory and you know how what we visualize on computer screens and through photographs might appear quite different. So that was really awesome. It was very cool stuff. Yep. So also, as Mallory mentioned, we try to do this kind of community news toward the end of these, just for a minute or two before folks log off. And this is to keep everybody in contact with each other, everyone informed about meetings coming up, or you know, potentially positions like PhD positions or career opportunities or postdocs or things like that, just so that we're sort of staying connected and staying involved. So I'll go ahead and share this month's community news. And of course, you know, if you have something that you'd like to contribute to this slide, you know, maybe a position that you're trying to hire for or a meeting that you're hosting that you'd like to kind of get the word out, let me know. I can always include it in the emails that go out to the listserv, and also the community news slide that we put in at the end here. And so I'll copy paste this into the chat. It's going to be just like a big gross bulk of text, so I apologize for that. But just so that y'all can click on the links that are in here. Oh my gosh, there we go. Okay, hopefully. Oh, there's a character limit now. Okay, well, I will do it one at a time. Sorry about that, everyone. Okay, so I'll do the first bit and then the second bit. Let's see, I think it's this. Didn't realize the Zoom chat had character limits now. Okay. Right, so next month we've got the Ice Giant System Seminar Series February edition, and so this will be Dr. Marzia Parisi from JPL Caltech giving a presentation, so make sure you catch that. There's also the FINEST, the Future Investigators in NASA, Earth and Space Science and Technology, so that's a graduate fellowship. Applications are due in just a couple weeks. EGU has abstract deadline tomorrow, but I think it's like really early in the day for US folks. So just check the timing there. So I believe it's, you know, if you're in the US or you have Pacific Coast or Eastern Coast time zone, you know, you might want to submit them this evening, because I think the timing is like early tomorrow morning, at least for us here in the US. And I included this in the listserv email that I sent out yesterday, but there's some folks, sort of grassroots community-driven questionnaire that a few individuals in the community are trying to get some information about for Uranus orbiter and probe science questions. And then there's this department chair position at UMass that's been up for, I think, a couple months now. So that one's still open. And then, of course, I appreciate that there's this community source list of folks looking for master's and PhD students. So if you are a student looking for a position, you would click that first link. If you are an individual looking to advertise your PhD position that you would like students to contact you, you would fill out that second link. Oh, and then I just saw in the chat, Krista Soderlund said the next OPAG. Oh, thank you. Yes, I forgot to include that. Sorry about that. The next OPAG meeting is February 25th to the 27th. Mark your calendars for that, and it'll be Tucson, but also virtual. And I believe that's everything that I have. So happy New Year. I'll turn things back over to Mallory to kind of close things out, but it's great to see everyone again, and thanks for joining.
Yeah, thanks, Jody. I did see one last question come in, and you got 30 seconds. From Danielle Wenkert, have you compared limb darkening from Voyager with spectral versions convolved with the filter / camera curves?
I think you asked me that already, and I said, yes, we've done that.
Oh, okay, well, perfect. Then we're at the top of the hour. Thank you again, and thank you to everyone for calling in, and have a great week. Take care.
Thanks. Bye.
Bye.
Bye, everyone. Thanks.
Thanks, everyone. Bye-bye.